Okay, folks. It's truly a pleasure for me to introduce today's speaker, who most of you already know because he's been here for some time as our visiting scholar. And one of the real fun things about being the director at CCOM, actually one of the few fun things, but is that as part of our program we have this visiting scholar program. So it lets us kind of search the world and try to find real experts in things that are important to us and invite them to come over here. And I think with Xavier we really hit the jackpot. We've been trying to get him here for some time, and we're thrilled that he's here. I think many of you have seen his background, but the thing that was news to me, I didn't realize it. Now I understand why he wanted to come here, because I hadn't realized that he got his PhD at the University of Maine, which is just up the road. Unbelievable. Yeah, so that's something. His PhD, it's University of Maine, Université de Maine. Le Mans, in France. If you read it, it's the University of Maine. I'll check. Yeah, his PhD was in physics, that's his undergraduate degree was, but it was the physics of brass musical instruments. That's it. And that's really quite neat because he's now doing other stuff, but another part or aspect of Xavier that I know, and I suspect many of you don't know, is that was not an accident, that topic. Because Xavier is a world-renowned flugelhorn player. Seriously, it has a jazz band that I've heard play many times, and they're quite excellent. And I'm hoping that before you depart, you'll get to hear your student brought your flugelhorn.
I did not, but...
Does anybody have a spare flugelhorn?
I'm sure you have one.
Really? Well, we'll find one for you. Or maybe an old trumpet or something.
We need entertainment for the CCOM Christmas party.
That's true. More seriously, and that is, I think research, he really is an excellent flugelhorn player, and it's jazz mostly. What Xavier brings here is really a phenomenal background. I meant to bring the books too, both the first edition and the second edition. I would say that he is probably the world's expert on multi-beam sonar and the interaction of sound in the seafloor. And you know, kind of everything we dabble in here and try to do, I find out, oh yeah, Lurton did that 10 years ago. Lurton did it better than so. And he doesn't tell us that. He's also very modest. No. So it is remarkable the kind of breadth of his experience of starting out with brass musical instruments and now applying it to the acoustics. And what's really neat is he sits on kind of both sides of both the theoretical side, understanding the theoretical acoustics, but also the very pragmatic engineering applications of it. And it's that kind of foot on each side, I think, which makes what he does so useful and so wonderful. And in doing that, he certainly has helped keep us honest as scientists, the whole community, but even more importantly, the manufacturers, because Xavier works very, very closely, I'm sure with great frustration, with some of the manufacturers to make sure that their systems produce data that we all benefit from. You're now today going to talk about something that we've all thought a lot about here, and that's not come up with a good answer. And we're hoping you'll have a good answer for the trade-off between accuracy and resolution. So thank you for being here.
Thank you very much, Rory, for this so positive and friendly introduction.
It's Friday, so Monday might be different.
Thank you to Garrett and Christy for inviting me to this series of seminars and for taking care of organizing everything. I'll begin my talk by a few elements about our background in IFREMER, about underwater acoustics, what are we doing there, and the way we interconnect with the CCOM activity actually. Well, underwater acoustics, as you know, as you should know, is the generic tool for ocean exploration and monitoring. And IFREMER, we are mainly a research institute in oceanography, so we are involved in most of domains of ocean science and technology, but we are also the national operator for the research fleet and facilities. And when I mean national, I mean for France, of course, but we are also involved in the European framework. IFREMER fleet is mainly 4 high-sea vessels of various sizes. The most recent being Pourquoi Pas. Coastal fleet, which is clearly less glorious, with older ships, well, not so performant, nor well equipped. And regarding underwater interventions, some interesting vehicles because they were really designed for our own purposes, such as no-till, an unmanned deep submarine, Victor, which was quite a breakthrough in the field of very deep ROV systems. Well, that's it. With this set of vessels and vehicles, all considered, that's about, because we are talking about multi-beam echo sounders here, roughly 12 multi-beam echo sounders that are operated today by our institute. So our objectives in the field of underwater acoustics is, well, to be good specialists of the domain, to get and to make work as good sensors as possible, to install them, to follow up them during their life cycle, to provide use methodology both to operators and to scientific users. We have a series of cooperations with industrial partners, with scientific teams. We also are very careful of conducting in a thorough way our own research and development activity. We have somehow marginal activity about the control of environment risks associated to the use of acoustic techniques, and the classical activity in the academic domain of publications, teaching in universities, advising PhD students, and so on. So for doing all this, we have mainly one dedicated team in Brest, 7 to 9%, depending on the number of PhD students that we are welcoming, and most of technical facilities for measurement of processing are in Brest too. Two main domains of activities: underwater engineering. So this is mostly related, of course, to the systems embarked on our vessels, but also to the R&D activity with manufacturers. We have the capability of designing transducers, not building them, but defining them in very details. And we go for at-sea trials or in-lab trials, acoustic measurements, and also modeling and system analysis of sonars. And this will be mainly what my talk is about today. Second domain of activity, acoustic data processing, that is aimed, as you may guess, at quality control of the data, at post-processing, applied to two main domains: seafloor bathymetry and imagery, and fishery acoustics. And we, in this respect, we develop our own tools, such as Sonar scopes that you have been introduced, certainly very relevantly by Jean-Marie Augustin when he was visiting scholar here, and Movies 3D, which is the software developed for data processing of fisheries echo sounders. All of these activities, of course, they meet very naturally some of yours, going from the field activity down to the most fundamental ones. The first constatation is that we operate more or less identical systems. And for instance, with NOAA, we have in common the use of the multi-beam fishery echo sounder ME70, the infamous 7111, that is installed, as far as I know, only on IFREMER and NOAA ships. Okay, but this gives us the opportunity to collaborate, to have a working group together, and that's really fun. And also, well, more current systems such as the EM 122, 1302, 1710, even Swath interferometers and so on. With and from this use of these systems, we have also the same issues for defining methodologies. Some raising issues today are the development of methods for monitoring the performances of the sonar systems, and in relation to the manufacturers conduct their maintenance. And so we have to develop, and you guys too have to do it, methodologies and software tools aimed at operators and users. A new topic that is raising too is sonar calibration, which is known for long in the field of bathymetry measurement, but which is less evident for imagery and backscatter measurement. And finally, we have, of course, all a series of common interest topics that are the today's up-to-date issues. One of the main ones being, of course, the use of data from the water column, but also the data quality assessment from sonars, the improvement of methods in bathymetry and reflectivity from the seafloor, and even fundamental topics in the field of backscatter, refraction, and so on. And hopefully some of these issues I am trying to address during the 6 months that I'm spending here. Okay, back to the topic of today's seminar. So the title is Bathymetry Measurements by Swath Sonar Systems. That's, of course, a huge topic, and I'll concentrate on a particular point, that's the trade-off between accuracy and resolution. So the summary of my talk will be roughly as follows. First, defining resolution for a Swath bathymetry sonar. Then a few elements about interferometry as a technique applied to sonar bathymetry. Then the heart of the topic, that's the trade-off between resolution and accuracy, illustrated by some simulations and case study of a particular sonar, and some perspectives before concluding. Let's go for a basic definition of resolution. If we go to this excellent Collins dictionary, 5th edition, we found quite a good definition, the ability to produce separate images of closely placed objects. That's nice. There's even a definition related to photography, that's the ability to show up fine detail in an image. That's good also for our sonar applications. So you can notice that in 2006, Mr. Collins was not yet aware of digital cameras. Okay, how do we apply this to Swath bathymetry sonars? Well, we have to go for a detour down to the very deep of the French popular culture. That's the pétanque game. Pétanque game, la pétanque, that's a variant of bowling games that you may find almost everywhere in the world, but that's a very important one in France. It's a very simple game. Basically, the goal is to throw metal balls that are as close as possible from a goal that is the jack, a smaller ball of different color. Every player has 3 balls. They are thrown in various in a predefined order and so on. And once all the balls have been thrown to the jack, then begins the really interesting part of the game. Everyone gathers around the set of balls, and then the discussions begin, because the score will depend on the ranking of the distances of the balls to the jack. And well, this is a very, very funny part of it, because well, that's a lot of eloquency, of bad face. It's really fantastic. And it's very popular. It's played. It's usually associated with people from the southern part of France, with retired people mainly, that you may find in every village playing this. Well, so you may ask, well, fine, but what is the relationship with multi-beam echo center? Of course, there is no relationship with multi-beam echo centers unless you decide to conduct a survey of a pétanque game with a multi-beam echo center. And this is exactly what we decided to do. Well, actually, it was not exactly, the goal was not to monitor the game by itself, but rather to test a new, at this time, a new system installed on our deep ROV. It was CBAT 7125 with very narrow beams, and the purpose was to check the resolution of it. So we had specially designed and built for us a set of boules de pétanque. Well, the only construction of it was really fun, because we went in contact with a national manufacturer, and we ordered them special boules de pétanque, which should resist to marine corrosion, which should withstand pressure of 6,000 meters, all types of requirements that they usually don't face. And the balls were installed on this target, a 2 meter long polymer plate with various spacings, with some rotation symmetry so that the heading of the sonar doesn't make a difference. And this was deployed in shallow water, 30 meters, and then in deep water, 4,000 meters. Yes. So this is still there now, actually. This makes it presumably the deepest pétanque gate ever. And here's the result. This is the DTM, digital driven model, of our pétanque game. Let's zoom in. And this is what resolution of multi-beam is about. You see that the central balls, they are separable by this particular sounder. I don't mention the altitude of the sounder was 10 meters. And the groups on the sides, they are not separable, they appear as undistinct groups. That's it. So with it, we have already a good perception of what resolution is about. Now, let's go to fundamentals. Sonar is a tool devoted to marine medium investigation according to two physical dimensions, time or range, and this is why a sonar uses short pulses, and angle, and this is why a sonar usually forms beams as narrow as possible. A particular C-floor mapping sonar provides two types of local measurements, ideally point measurements, soundings, altitude Z, or depth Z, and intensity for sonar images. And all these local data, they are used to feed 2D presentations that are at the ultimate step, bathymetry charts and reflectivity maps. So, in the case of C-floor mapping sonar, we will reserve the appellation of accuracy to this measurement, this local measurement of Z, say, and resolution is the separating power in the two dimensions. In the time domain, the resolution of the sonar is given by its ability to separate two distinct targets according to range, and this condition of separability is given by the fact that the delay between the two echoes from the two targets are or are not longer than the duration of the transmitted pulse. And expressing this with basic equations, we find the signal resolution I as a magical formula CT upon 2, C sound speed in the water, T the pulse duration, and the upon 2 because the signal is a two-way one. Time resolution is not to be confused with the signal sampling rate. If you consider sampling such echoes, whatever the sampling rate that you impose, of course it's better to increase the sampling rate, but it does not improve your capability to separate the two targets. It's just a better description of a waveform that is basically confused.
What about the inverse of it? The inverse, if your sampling time is too long,
Yes.
won't that affect your resolution?
Then resolution, if resolution is longer than the pulse length, which is not to recommend.
No, of course not, but it happens.
Then of course the resolution will be the sampling rate. Yeah. Okay. But normally it's not the case. Even the worst constructors know about it. Okay, now in the angle domain, let's take the very easy example of the single beam echo sounder. A single beam echo sounder, inside the beam, the confusion, the ambiguity volume is given in one direction by the pulse length, which is always the same, and in the horizontal direction by this section, which is related to the beam aperture. And in this we see the main problem associated with beam aperture. It is that the resulting resolution is not constant with range. So we are facing a varying resolution in space. So at this step, we know already a lot of things. We know that in the range or time domain, the resolution of an echo sounder is given by its duration, the signal duration. So normally it is constant all over space. It causes some distortion of targets due to the lengthening of the target echo by the signal length, and it has nothing to do with the sampling rate. In the angle domain, the resolution is the beam width. This beam width raises a resolution that is anisotropic, varying with range. It may distort in a strong way the target's apparent shape, and it has nothing to do neither with beam spacing nor with the number of beams. And I insist on this because very often, to say the least, in commercial literature about sonars, you will find resolution which is announced and which is actually either the sampling rate or the beam width. And it's quite hard to make the constructors change their mind because, of course, the figures for sampling rate and beam spacing is usually much better than the pulse length or the beam width.
Xavier, do you think that that's in part because of a misunderstanding with the term resolution? That
yes.
That it's
yes.
Okay.
I
I mean, I've seen resolution described as your ability to detect an object as opposed to distinguish it from other objects, and that's a different thing that might depend on sampling rate.
No, yes, but resolution has the ability to detect an object. It is in my opinion, practically impossible to quantify. Because you can imagine a very small target with a very high target strength. For instance, a bubble of air inside water. As small as it is, it may raise a very significant echo. So it may be detected absolutely whatever the pulse length, the beam width, and so on. So I'm not very comfortable about this idea of capability of detecting. See? Something is missing in this notion. While being able to separate two targets, well, this makes sense. Now let's go a bit deeper in the description, the modeling of it. Starting with the side scan sonar, which is quite easy. The ambiguity surface that is associated to the sonar working depends in the along track direction on the aperture of the beam and in the across track direction, y, on the signal length. So dy is CCOM-2 projected on the seafloor via the angle theta, and delta x is related to the horizontal aperture phi and projected on the seafloor. So this is strongly anisotropic, and the resolution inside the swath of a side scan sonar changes dramatically from the center of it to the ends, with the proportions of the ambiguity surface that are completely modified from one end to another. For multi-beam echo sounders, well, it gets a bit more complicated because we have this notion of the beam footprint onto the seafloor. So basically, the ambiguity surface is now the projection of the beam itself onto the seafloor, but with also some influence of the signal, and the actual resolution will depend on a mix between the two and from the processing that is applied to this. Along track, the resolution is the same as for side scan sonar, and across track then begins the complications. But what we can say is that resolution in this across track direction will be always worse than the lower limit, that is the signal length. It cannot be better than that. And it cannot be worse than the projection of the whole beam onto the seafloor. So the actual resolution is somewhere between these two. And so depending on processing will favor rather a high resolution detection will have an ambiguity surface this way, or a low resolution processing will have an ambiguity surface which will look like that. Okay, so we know now that for multi-beam echo sounders, the resolution is essentially a matter of beam width. If we go back to our favorite game, we compute easily that for the 1 degree beam that is the one of this particular sonar at a range of 10 meters, the resolution is 17 centimeters. Now, what about the target, the inter-target spacing? It is nominally 20 centimeters minus the diameter of the balls, that's 12 centimeters. So obviously, with a 17 centimeter resolution, you are not able to detect gaps that are only 12. So the 40 centimeter spacing that this one can be resolved, the 20 cannot. And also interesting is that the actual, the apparent target size is quite bigger than the actual one. It looks like about 25 centimeter balls. That is not practical at all. And so that's merely the summation between the beam aperture and the actual target size. These discs represent roughly the size of a 1 degree circular beam. Actually, the beams are not circular, but it gives the order of magnitude of a 1 degree beam projected onto the seafloor, and this show you easily why some targets are separated and others are not. Okay, now an illustration with more usual data from the seafloor. We have the chance to have available data from the same area surveyed by 3 sounders at different times. One of them was historical EM12, one of the first multi-beam echo sounders installed on a research vessel with beams 2.5 degrees. And then the Reson CBAT 7150, which works with beams both of 1 degree and half a degree. And all the data are processed using the same tools. This first example is from the so-called Black Mud Canyon. That's a zone at the foot of the Continental Rise in southern Brittany. And here the data is, depth comprised between 3,600 and 4,400 meters. This is the data from the EM12, 2.5 degrees, 1 degree, 0.5 degrees. The same area at a different scale with now depth ranging from typically 1,000 meters down to 4,000 meters, 2.5 degrees, 1 degree, 0.5 degrees. Very demonstrative. This one is in the abyssal plain, close to this Black Mud Canyon. The so-called Withered Canyon, which is not a canyon at all, that's merely a trench about 50 meters deep and at a depth of about 4,500 meters. 2.5 degrees, 1 degree, 0.5 degrees. Clearly you are not seeing the same thing with these different standards.
Do you have some sort of DCT artifact in the low resolution one there? You've got this grid pattern. If you go back to the low resolution.
Yes, this is linked to the post-processing of the data. Okay, so what have we seen? We have seen that, well, basically the problem is beam width 1, so the solution is trivial. Let's build sounders with very narrow beams and let's purchase and use them. But as you say here, there is not such thing as a free meal, that's it. And there is a price to pay for it. It means this policy that you will have to deal with many narrow beams. If you go to this CBAT 7150, the constructor designed a sounder dealing with more than 3,000 beams per peak. That's a lot. Especially considering that most of the data from it are watch. This leads to quite long arrays. for having a 1 degree resolution at 12 kilohertz means 8 meters away. A long ship, it's acceptable. A cross ship, it raises serious problems. And the processing load is in correspondence with this. So the issues that we are entitled to raise are: is this cost both technological and economical? Is it worthwhile? Why so many beams? What is so special in getting those individual beams and so many of them? And so, what about the systems that form no beams and work as well? Okay, so our investigation will be how is classically measured, I mean in standard systems, the sounding inside one given beam. Why is the sounding unique, and does it have to be unique? What is the resolution that is associated with this measurement? What is the possible conflict with accuracy of this resolution? And how can we improve this concept? We'll go first by reminding some fundamentals about interferometry. The basic principle of interferometry is that the echo raised by a target point will arrive on a basic receiver consisting of 2 sensors, and the measurement is the phase difference between the signals rising from these 2 sensors. This phase difference may be expressed as a ratio between the interferometer spacing, the range between A and B, the wavelength of the signal, and the steering angle related to the interferometer axis. From this phase measurement, we can retrieve the angle of arrival, zeta, and having both zeta and r, which is nothing more than the time of propagation to wave, we are able to reconstruct the position of the sounding point. Well, this is a very straightforward and powerful method of measurement, but the problem is that it is very sensitive to noise. And there are many causes for noise to perturb this measurement. First, the backscattered signal from the seafloor is intrinsically fluctuating due to various physical phenomena on the interface. And also, we have to consider additive noise, either electrical or acoustical, that superimposes to the useful signal. And the effect on the accuracy of the phase measurement is dramatic. If you consider this curve, it gives the evolution of the error on a phase measurement as a function of the signal-to-noise ratio. Consider a signal-to-noise ratio of 10 dBs, which is not very much, but which is not exceptional either as a situation. 10 dBs. The standard deviation of the noise of the phase measurement will be 40 degrees. That's a lot, especially considering that the maximum error that you can do is about 100 degrees. And in this case, you are not measuring anything, you are just processing noise. Okay, this phase error will impact either an angle error or a time error depending on the type of sonar. In turn, this will give a bathymetry error that will depend either on angle or time error themselves related to phase. To combat this problem, there is a very classical solution in signal processing, whatever the application. When you have noisy signals, what you do is you stack a number of them, and this enhances the good part of the signal, and in proportion it lowers the noise impact. So this is what we are doing here. we are then trying to average this noisy signal over n independent realizations. In radar, this is known as multi-look processing. And in radar, it is very comfortable because you have such a high rate of pinging and you have so stable scenes that indeed you can stack a series of images, of snapshots of the same scene in a very coherent way. In Sonar, it's not possible. We are passing one time over a target and that's done. So we have to cheat. And this cheating is done by averaging not over several times the same scene, but inside one scene, averaging neighboring samples. Not so good, but it works. And it can be shown that the phase variance when using signals averaged over n realizations, it varies in the good direction, of course, with n and transformed into a relative depth error. The depth error is proportional to the inverse of the number of samples. This network of curves, it shows the same than previously, the error in phase as a function of the signal-to-noise ratio for 1 to 100 samples considered. And you see that for the same 10 dB signal-to-noise ratio, with 100 samples, we are now at a phase error of 2 degrees instead of 40. That's good. But once again, it's not so easy, because for obtaining this result, we have been averaging over these neighboring samples, and so for gaining square root of n in accuracy, we are losing n in resolution. How is this met in a practical multi-beam interferometry? Well, the interferometric processing in the multi-beam echo sounder, it is invariably made this way. The receiver array, which is typically horizontal, is split into two parts, subarrays forming subbeams in the nominal direction zeta O. And the signals from these two subarrays, they are used for computing the phase difference, and this phase difference, in its useful part, that corresponds to the common part on the seafloor of the two subbeams. This useful part, it is a quite regular so-called phase ramp that goes from -pi to +pi. And the processing that is invariably applied in multi-beam echo sounders consists in fitting over this purple ramp here an ideal polynomial shape that is usually a straight line, and detecting the point of zero crossing, of zero phase difference crossing. When we have got this instant, the problem is solved because we have an instant of detection, we have an angle, and so we have the sounding point here. This is a very nice method, and it has plenty of advantages. Using those narrow beams, it improves the signal-to-noise ratio. There is no phase difference ambiguities in the interferometric processing. This way of detecting the zero crossing time, it's both accurate and robust, but the resolution that is associated with it is very low. And why is it so? Because for doing this, we have been fitting this ideal green line over this length, meaning that we are not really doing a local measurement, but we are using all the information comprised in this interval in order to get this oblique point. And this is a weak feature of this method. For the other type of interferometric systems, namely the interferometric side-scan sonars, the configuration is a bit different. We have now two sensors, typically vertically disposed, and they have no special directivity. The phase difference is computed between those two sensors and plotted as a function of time. And for every time sample of this curve, one computes from this phase value, one computes the angle associated with the phase value. And so for each time sample, there is one angle and hence one sounding point. Obvious advantage, one sounding per time sample, very high resolution, as high as possible. But there are some shortcomings. The most annoying one being that the signal is very noisy. You remember the 40 degrees of error at 10 dBs. And so the data points, they are normally not usable this way, and some averaging, some filtering has to be applied there. So to summarize, multi-beam echo sounders, we are working at fixed angle, measuring a time, good accuracy, poor resolution. Interferometric side scans, we are working at fixed time values. We are measuring angles, poor accuracy, but a very good resolution. So what can be done? What can be done from this? Having integrated this concept that finally the resolution is linked to the phase ramp length, what can we do? The first solution is, well, the one that was chosen by Reason for the latest generation of systems. It's some brutal force solution. It's to decrease the aperture of the beams. Well, the beams are narrower, so the phase ramps are shorter. A more clever solution is keeping the same beam width. It's to decrease the width of the phase ramp interval that is used for fitting. And the first trial, I participated in it. It was about 12 years ago, and with Kjell Nielsen, who is an engineer at Kongsberg, we designed for our EM300 an optional feature that made possible for the operator to shrink at will the width of the phase ramp. And following some further R&D works that we conducted at IFREMER, Kongsberg implemented the so-called high-resolution mode, first on the EM3002. Now it seems that it has been extended to other sounders. And the idea now is not only reduce the size of the central part of the phase ramp, but also take advantage of the lateral parts of it. And in this way, you are able to define inside one beam, not only one, but 3, 5 sounding points. And this is a major breakthrough. Here are some results of simulations that I run in this perspective in order to demonstrate the interest of improving the resolution associated to this interferometric process. The basis of the simulation is very classical, using simulated seafloor topography, which is described by discrete point scatterers, each one sending a coherent return signal to receivers. Beams are formed, the phase ramp is computed between the simulated beams and so on. And finally, fitting the straight line, estimating the zero phase instant, and finally getting an estimated seafloor profile, which is compared to the real seafloor profile. And this can then be applied to a variety of configuration of depths, beam widths, sampling rate, and so on. Well, just one example of result. A shallow water system with, on the seafloor, two features, two bumps, 12 meters by 2 meters. And the estimated seafloor is computed using the standard interferometric multi-beam process by using a phase ramp that is the full range of the footprint, or 1/2 of it, or 1/4 of it. And you see clearly what is the advantage and the shortcoming of reducing the phase ramp length. In this case, 100% of footprint, you have quite a stable signal. The signal-to-noise ratio is not very good, 10 dB. Quite a good accuracy of the signal detection, but a very poor description of this target that is in oblique incidence. You decrease the footprint, you increase the resolution, and you go to a better description of it. And finally, with 1/4 of the footprint, well, you have a nice description of the feature, but your noise level has increased. So is it acceptable or not? Well, it depends on your requirements. So again, one more illustration of this trade-off between the two concepts. Presenting it in a 2D representation, for instance, what can be seen by multi-beam echo sounder over a field of sound waves. So these are very naive sound waves, sinusoidal ones, sine ones, I mean. And this is the real topography, and this is the same topography as seen by multi-beam echo sounder, interferometric, working with phase ramps of 100% of the beam width. If the beams now are 2 degrees instead of 3 degrees as previously, 2 degrees, that's better. 1 degree, even better. And we go to half a degree, and well, it's getting good. And we are not yet fully happy about it because there are some sampling artifacts, but we have only 200 beams. So if we go to a very rich system, resin-like, with a high number of beams, yes, we are getting a representation of the scene that sounds correct. We can apply it to demonstration of the interest of going on one configuration from 100% of phase ramp down to 1/4 of it. You see that the improvement of the representation of the roughness features on the sides. This is the same, including the noise level. Okay, so to summarize these results, the across-track resolution of a multi-beam system is given by the physical length of the fitting interval. This is a very strong conclusion to remind. So you can think of this resolution as very simply a smoothing filter that you imagine applied directly on the seafloor topography. The parametric study that I conducted showed a number of things, that other parameters impact also on the quality of the final estimated topography, was beam width, sampling frequency, beam density, but none of them really impact on the actual resolution. And this is illustrated by a fine case study corresponding to the installation of a new EM 3002 on board research vessel Belgica that is used by our colleagues of the federal government of Belgium. By the way, they've got a new government in Belgium after 15 months without a government. It was great. This is the type of data, type of application that they work on. This is in quite shallow water, typically 30 meters. Really wonderful landscapes of sand waves and dunes. So in the North Sea, that's it. And their purpose is to regularly survey again and again this area in order to see the evolution of the topography due mainly to sand extraction activity. You see here, that's an area of sand extraction. And so typically they survey up to 4 times a year the same area, and with, of course, accuracies of measurements that have to be very good.
Is that what those kind of wedge-looking things are? You're talking about the sand extraction?
Yes, that's this
Okay.
this area here. You see where all the regularity of the natural dunes is completely messed up. Okay, so they choose to replace their old EM 1002 by a brand new 3002, and after installation, this is what they got. Very disappointing, because on sand dune or sand wave rather zone, they got a nice representation of the waves here, and on the sides, just notes. So the things went worse because, from their point of view, they were, of course, not happy at all, because the sounder was not able to do what they intend to survey, to monitor. But from the constructor point of view, everything was fine, because the constructor, he knows only about the sounding accuracy. The sounding accuracy, it is checked on the flat sea floor without any details, and he measures the standard deviation of the soundings. This was compliant with specifications, so everything was okay. So the situation was completely blocked, and well, we were asked at IFREMER to intervene as referees in this case, and well, I processed the simulation I showed you before with the same parameters as the ones in the actual survey. And this is what I found. So this was a demonstration that using a phase ramp of 100%, the sounder was not able, whatever the other parameters could be, the sounder was not able to see what happened on the side. So the people were searching, both the customer and the manufacturer, problem in accuracy of measurement. It was not, it was a problem of resolution of the measurement. And so this was transmitted to Kongsberg, and finally, well, they admitted that they were working with too long phase ramp length fitting. They provided a new release of the system. These ones were checked and adjusted at sea by the operators, and finally, the results were good again, and everyone is happy. That's it. So I'm speeding up. The main conclusions about these issues of interferometry accuracy and resolution. Averaging time samples is a need for getting a decent accuracy of measurement, but this is detrimental to resolution. The zero phase difference is not a local measurement. This is something that is hard to integrate for many people, but you have to be convinced of this. Even if it crosses a straight line with the time axis, it's not a point measurement. It integrates actually a whole set of data that covers a part of the seafloor. So adjustable or correctly adjusted fitting is of high importance. And bathymetry resolution should be considered as important as accuracy is today. And this is not the case, actually. For instance, in the IHO recommendation, this aspect of things is discarded. So some standardization of this aspect should be needed. To end with it, what can we pull out as conclusions and perspective for the engineering of multi-beam echo sounders? First one is that the dogma of one beam, one sounding is not a necessity, and it is rather justified by the weight of past history rather than by actual technical constraints. Several soundings per beam are possible, and narrow beams across track are not actually mandatory. And a good concept could be to mix the two designs of multi-beam and interferometric side scan. The idea would be to form a limited number of beams, reasonably narrow, and inside these beams to process side scan-like time interferometry in order to get as good a resolution as possible. So should meet the best of two worlds. And R&D works are underway, and especially I know that here in CCOM, Tom Weber is working on such issues, and at IFREMER we have also people working on this concept. So the dream is to imagine future systems that should be lighter with shorter arrays and possibly even better resolution than we have today. So where do we go from here? Well, obviously some research and development works have to be conducted still. And we are lucky because we have opportunities to get data both from dedicated systems that are able to process the bathymetry data on a multi-beam, a classical multi-beam point of view, or an interferometric point of view, and this is the case of the fisheries ME70. Or we may also use classical multi-beam echo sounders using the logging of the raw data from the array staves. We have to insist upon manufacturers so that they improve resolution for the multi-beam constructors, so that they improve the accuracy for the interferometer manufacturers, to suggest to the competent authorities that something about resolution requirements should be good. And an important point is to imagine and to design procedures for this resolution assessment. And this brings me to the end of my talk, and I'll be glad to answer your questions.
Fire away. So in the real world, if I'm out on with a EM122, what criteria do I use to shorten the ramp, the phase ramp? What criteria do you, just the image? You just look at the image and see if it improves, or do you have like a quarter of the ramp centered on the zero phase, or?
The ideal setting is to adjust the phase ramp according to the spacing between the sounding points. Your EM 122, it will give you 400?
432, yeah.
Something like that?
Yeah.
Okay, so this gives you an idea of the range sampling on the seafloor. Ideally, if you have phase ramp intervals that correspond to this spacing, then you will get independent soundings, because this is the key point, that you have one sounding independent from the next one.
Yeah.
Well, practically, this may be too demanding. This can lead to too short ramps. In this case, your noise level will increase. So you have to find some compromise for the level of resolution and the level of noise that you are disposed to accept. There is no unique answer to this.
So you would do this in a patch test, then you try to
Yes.
decide before you started actually collecting data. We don't really collect the raw waveforms very much.
You don't have to go to the raw waveforms.
Isn't it true that practically with the system, you have the choice of either high density beamforming or not? I don't think you can, without going into the
I
manufacturer's.
don't think you can tune it, yeah.
I don't-
You can't tune it yet.
In the new version of SIS, there's a phase ramp setting, but I don't really understand it yet.
There's a phase ramp setting.
Yeah.
Yeah, that's it.
In 382 or 383.
Okay, well, I wasn't on that either, so.
But we did change the phase ramp though.
Yeah, but it was just, it was kind of long and short, basically. We didn't have.
There were three choices, weren't there?
Medium.
Yeah, maybe three.
But it's not that you can sit there and tune a phase
No,
ramp.
they were fixed choices.
Yeah.
Huh.
Are they explained in the manual, you know? What the settings changes do?
Well, that's just what Sally was describing.
Yeah.
Gives you a long phase ramp, or shorter or medium.
Sure.
Hmm.
Okay.
I have a question. The same kind of simulation you did for the phase ramp change,
Yeah.
have you done that on the other side for how much averaging in a IFREMETRIC side scan sonar system is needed to get an optimal?
I did not apply it to this particular case, but well, obviously the physical problem and the programming are exactly the same, so you can need them, of course.
I know, I was just thinking for some things that we've been stuck with, that, you know,
Yeah.
knowing where to optimize that in, that would be very, 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 very useful too.
It
An
sounds
important
like-
part of that question is what do you mean by an optimal result, right?
Well,
Different things to
that's
different
exactly
people.
right, but
Yes,
but you look at the same plots.
typically,
of
this
stuff
is
you
the question
produce.
by Jim.
Yeah.
When do you decide that you have correctly optimized your system via the phase one?
But if you see the trade-offs. does that
For
make you
instance,
table?
the Belgian colleagues, they had to tune it at sea in order to arrive to a satisfactory result. But they knew more or less what they wanted to see, so this helps.
How did the accuracy change? Like if you look at the mean surface, did you see a difference in Mark Roche's data?
About the accuracy?
Yeah, when you told them to change, or even in your simulation, what was the trade-off? If you cut it down to a quarter of the ramp, phase ramp,
Yeah.
what did it do to the surface in terms of the, I don't know how you even test it, but the sort of like the mean or even individual?
I don't have these results, and I'm not even sure that they did take the problem this way, because actually what should be done is once you are happy with some resolution, you should have to go back to accuracy measurements and to replay the patch test again, and in order to see how high your uncertainty on the soundings has increased, because it has to increase.
But you can do it on your simulation, then.
Yes,
You can simulate.
yes, it's but well, I can certainly play it again, but I cannot answer you at the minute.
I just want to make a comment. You brought up the ME70 and the fact that we do this and you guys do this. Laurent, I guess, does this with the you know, the sort of hybrid multi-beam interferometric method. What the advantage that the ME70 has, I think, over other systems, it has some disadvantages, but what makes it work so well with that system is it has a really high signal noise ratio, like really high. It's designed with very strict criteria to go look at small fish and things like that, so it has a very high dynamic range and the self noise is very, very low. And I feel like and I'm just guessing at this because I haven't exactly done an analysis, but it seems to me that some of the interferometric side scan manufacturers have not caught on to this.
Yeah.
That they are designing, they have noisy electronics and things like that, and their systems would work much, much better if they put their money at that signal noise ratio problem, and we would get much better results. There's some other differences too, like the beam width is wider, so you have a larger footprint on the seafloor, so you get more of a signal return. On the other hand, the ME70 puts out a very low source level. So I really think a lot of it is signal noise ratio, and I feel like some of the manufacturers should catch on to that.
The other strong point of the ME70 is that the beam directivity is very carefully done, and the level of side lobes and so on is really very well controlled, and this adds a lot to the quality of the interferometry. So
Somebody else, I'll keep going. I guess I just wanted to throw out a point for our students mostly, which comes back to resolution and your picture of the buoys, the multi-beam image, that everything Xavier said is obviously true, but all of us have to be very careful at the end of the day when we think about things like resolution when you display it. Because how you grid the data, after all this hard work to do the sonar engineering right and to do the processing right, at the end of the day you can destroy it all if you don't appropriately display the data, and you have to grid the data, and those data were gridded, I assume, in your image, and display it somehow, and you can actually just ruin it all that way. So remember that there's another aspect to that final resolution when you look at it in an image like that, in terms of how you gridded it, you have to appropriately grid it, and how you finally display it. Nothing more?
all right, thanks, Xavier.
Nice.